All right, so the ladder of powers on the TI-84, okay? So this is just one variable. It's not a line that we're going to try and straighten. I'll look at that in a second. But notice, when you start out with x and y, this is skewed to the right. And so we try squaring, and you're like, oh, it just got more skewed to the right. And then you try cubing, it would get even more skewed, okay? So that's not what you want to do. So you're going in the wrong direction. It skews things to the right when you go increase your y, okay? But if you go the other way, oh, it's making my box bigger, and a data point appears on the left side. So that's actually getting better. Oh my goodness, look how like symmetric this one looks. And then if I kept going, it's actually skewing it to the left, okay, towards the smaller numbers down here on my scale. And so your goal is to try and find the power that makes it symmetric. We're always starting here. Y equals, okay? But you can square your y's, you can cube your y's, you can square root your y's, you can log your y's, or natural log. It doesn't matter what base you use, okay? You can do -1/2, -1, or -2 as your exponent, okay? So you want to test those out, and let's try it. The video you watched was very sort of like idea-y, but it wasn't practical for how we actually re-express data on the calculator. So this is data of processor and the number of transistors that it had from 1971 all the way up through 2000. And so this is what the equation is going to come out to, and I'll sort of show you what happens. So I enter all my data into my calculator. And if I turn on StatPlot, what I find is that it is not linear, okay? So we want to try re-expressing our data. And so it's relatively easy to change my data. Now, I don't want to mess up my L2 because that's my actual y's, but I can let this equal L2 squared. Boom, I just squared all of my data. And now when I do my scatter plot, I want to graph L1 and L3 because that's where my y squared is, okay? And then if I go here, I can hit zoom 9, boom. Oh, that made it even worse. Like it flattened it out and made this even steeper. Guess what would happen if I cubed it? It would make it even worse. So now, instead of going up towards cubing, we're like, wait, I was at 1, I squared it, it got worse. Well, let's go down and square root it. So if I go into stat, edit, and I switch this to be the square root of L2, now I'm taking the square root of all my y's. And if I do zoom 9, ooh, look, the points like lifted off the axis. They're starting to straighten out. Well, let's do it again. Stat, edit, change it to natural log, or here, I'll even do log of L2, okay? And hit enter, zoom 9. Look at that, there's like 1 point out of place, but everything else looks practically perfect in every way. If I do stat, edit, that was a Mary Poppins quote in case you're wondering. If I do this as second L2 to the -1, okay? So that's taking the inverse of everything. Then if I do zoom 9, notice it's actually bent it the other direction, and that's the problem. That's where we start running into problems. All right. So the perfect one was natural log or logarithm. Okay. So if I go stat, edit, and I change this to ln of L2. No, second 2 does L2, second 2, ln of L2, and we see that zoom 9, practically perfect. Just looks like the logarithm, okay? So that's my ladder of powers. And then if I do stat calc, lin reg, I want to go from L1 and L3, okay? But, and I can store this in y1 if I want, oh, wrong button. I want to hit vars, y vars, okay? So if I do this, it's creating for me a nice linear regression equation, which is what I have right there, the 0.33 and the 7 point. Oh, it's off. Maybe I have a typo, but we'll use that equation on my other page. So what's happening now is when I graph this, it's going right through the data points, okay? And it's a great predictor, except for that one stinking point. That's probably a typo. All right. Using our equation, though, it's not really a y equals. This is ln of y that I've actually put in there. And so my equation is natural log of predicted transistors equals 0.33 times years after 1970 plus 7.41. Okay? And so when I want to calculate something, when will we hit 1 billion transistors? I can plug in the predicted 1 billion, and what I'll type in here is ln of 1 billion, which is 10 to the ninth, equals 0.33 times years plus 7.41. And if I subtract 7.41 and divide by 0.33, I'll do that on my calculator. So I'll take ln, I'll go to my home screen, natural log of 10 to the ninth minus 7.41. Okay, and then divided by 0.33. That's my coefficient. And so I get the years is 40 years. And so that's 40 years after 1970. Okay, so years equals 40, which is the year 2010, is the year that I expect to hit 1 billion transistors on a single processor, which is crazy. How many transistors do we expect in 2020? So now we have ln of predicted transistors equals 0.33 times, that's 50 years, okay, because I started in 1970 was 0, plus 7.41. And if I simplify that out, we're looking at 0.33 times 50 plus 7.41. And that's 23.91. So I have a natural log, and this is the hardest math you'll have to do all year. Transistor hat equals 23.91. And how do you unlock this logarithm? Well, if I put a base e on both sides, now we have e to the ln of my predicted transistors equals e to the 23.91. The e and the ln cancel each other out, and I get my predicted transistors. So I'll put it up here. Transistors hat equals whatever e to my answer on the calculator is, which we see right here. So I can do e to the, no, I want to do e second ln, and then I'll do second answer. Oh, and I get 2.4 E10. So it's 24 years later. So we'd expect to hit, we'd expect to be at E10. So that's 24 billion transistors is what we're expecting to be at in 2010. Okay. 2.4 with 2.4 times 10 to the 10th, which is 24 billion transistors is the final estimate. And you can go and check online and see that we're actually pretty close to those numbers. I think we hit 40 billion transistors recently, just with one company. So good luck and farewell.